So let's go through present value. So present value, like we spoke about a little earlier, when we're calculating present value, we're figuring out how much something is worth today in terms of a payment you would get down the road. So think of this like an account where someone gives an inheritance for you to maybe go to school with. Okay, maybe they drop $10,000 in the bank, and then every month you're able to take $100 out for so many years. Okay, a little different than how we usually put things. When we talk about a regular payment, we usually think of actually paying that money to the bank. But our regular payments are what our bank account is going to pay us every single compounding period. I say month, but it's technically compounding period. So we're going to try two different examples here. And what we're going to try to figure out is if we were to live for 80 years, and we got an interest rate that's compounded monthly, in our first example, we're going to take $2,000 a month and see how much money we would have to invest right now to live this way. Okay, in our second example, we're going to get $4,000 a month, and we're going to see how much money we would need right now, so how much money to put into the bank account right now to live for 80 years getting $4,000 a month. Now, we do need an interest rate. We didn't talk about that. We're going to make a bold assumption here. We're going to assume that because we have such a large sum of money, we don't know what it is yet, that the bank's going to give us a pretty good interest rate. I think the bank can borrow money at around 2.5%. So we're going to say we can get at least a 2%, maybe even a 2.5%. So let's go with 2%. Okay? So we're in some account that gives us an interest rate. Kind of dragging. An interest rate of 2%, which means as a decimal that's 0.02. Okay? And this account compounds things monthly. Okay, so our compound period is monthly. So we have to define all of our variables here. First of all, we'll call this example A, and this one will be B. In example A, our regular payments are $2,000. Our compounding period is going to be monthly, which is important because that's going to help us calculate I and N, if you guys remember. From yesterday, in order to calculate I, we need to take the compound period, and we have to divide it by, sorry, wrong way around. We got to take the interest rate and divide it by the compound period. So R being our interest rate is 2%, and our compound period is monthly. Oh, it's over here. Okay. So we'll have to take 2% and divide it by, what is monthly? What number represents that? 12, right? We're talking about 2%, and I should put this in per year. It's dragging quite a bit. Per year, so it's going to be 12 times a year. Our N is also a formula. N is equal to the number of years. In this case, we're deciding to do this for 80 years. So it's our number of years times our compound period. And that's going to tell us the number of periods, how many times we withdraw money over the course of 80 years. So if you guys have those TVM solvers, let's see if you guys can plug it in right now and try to get it. We're going to work through this with the formula.
Stupid BlackBerry. Sir, I know.
So we have to figure out each of these things. We're solving for present value. Our regular payments are $2,000 a month. Okay.
What's the issue with BlackBerry World? Wasn't it?
We take 1, subtract 1, plus. Now we have to calculate I. We'll do that on the side. I is equal to 0.02 divided by 12. Okay. That's going to give us a decimal number. So for now, I'm going to leave it as a fraction. We'll calculate that in a second. We'll figure that out too. To the power of, and this is technically, if you guys look, very different from our other formula. This is a negative exponent, so negative n. And we have to figure out what our n is. 960? Good. We'll put down what the numbers were first that we needed to solve that. But it's going to be negative 80 times 12. And all of this is divided by I, which we already calculated as a fraction to be 0.02 divided by 12. So we'll go this one step at a time here. So our present value is 2,000. 1. We're going to figure out this value here of 0.02 divided by 12. So our I is 2 zeros and then 1 6 repeated. So 0. So I'm going to do this all in one step. If I add the number 1 to that, and I'll show you in the calculator, if we add the number 1, all we're going to get is a 1 in the 1's place. So we'll say plus 1 equals 1.0016 repeated. So 1.0016 repeated. The repeat is going to be important because it's going to keep us very accurate with what we're doing. Our 80 times 12, what did we say it was here? 960. So negative 960. And all of this is divided by our I, which we just calculated to be 0.0016 repeated. Okay? So we'll continue this. 1 subtract this value here. Does anyone know what that's going to be?
0.0016.
Yeah. But before I do that, what do I have to do?
Multiply by negative.
Power of negative 960. That's a very large pattern. Okay? So I'm going to put this to the power of 960 when it's negative. Okay? So negative 960 is equal to 0.2021. So our next line reads 2,000 with 1 subtracted by, and we'll take our number here, 0.2021. 2021. Still divided by our 0.0016. Repeat it. Okay. We're then going to work with our brackets. We have to take 1, subtract that number. Am I able to do that in this case? Yes. If I make this negative and then add 1, give me an answer. Okay. 1 subtract that value is 0.7978. So 2,000 times 0.7978. Still, this is all divided by our value is 0.0016 repeated. We're going to multiply the top and then divide all in one step to find out how much money we would need right now to live this way. So multiply this by 2,000. And then I divide it by 0.001 with a lot of 6s. So I'll try to put as many in as possible as I can in this calculator. Is equal to, wow, that's a pretty small amount of money. $957,401. $957,401, and I'm not sure what the cents were, but according to this, to live off of $2,000 every month, we need to put in $950,000. So $50,000 short of $1 million, assuming we get this interest rate. It's not bad. It's a large sum of money to put in right now, but a little less than we expected. Now, let's try this exact same formula, okay? And the only difference is going to be I can go right into this point here. So let's show how we can jump ahead and compare this. I've done all of this work here. The only number we want to change now is the amount of money we're going to live off of. Instead, we want to try to live off of $4,000 a month. So, in this example, these values are all the same. The only difference is this number is $4,000. So we take 4,000 and multiply it by this.
Would it be incorrect to assume to just double that 900? Yeah, it would be incorrect because the interest would...
The interest is going to change it, and let's see how much it's going to change it in this case. So we'll do this last step again, this time using the number 4,000. So we had 0.7978 times 4,000 divided by 0, 0. And in this case, we need 1,914,720. 1,914,720. So in our second case, if we were to win $2 million, assuming we could get this bank account, we can live off $4,000 a month. That's a lot less than I thought we needed. So, in this one, we were taking out $2,000 a month, and we're going to figure out how many times we did that. And that's actually this number here. This is the number of times we withdrew money from the bank. 960. That's the number of periods there were. So let's actually figure out how much money we took out of the bank. If we were getting $2,000 every time we withdrew, and we withdrew that amount 960 times, how much money do we get? Times 2,000. So we actually took out 1.9, is that right? Yeah, $1.92 million. So 1,920,000. I want you guys to compare this. This is how much money we put into the bank. We put in less than $1 million, but we were able to withdraw closer to $2 million. The same idea is present here. We were taking out 4,000, and we did it 960 times. We actually got $3.84 million. So, if we were able to put in this $1.9 million, after 80 years, we would have withdrawn $3.8 million, a much larger amount than we originally put in the bank. So we were able to spend a lot more money than we originally invested into the bank.